Hi calculus students. In this video we're going to talk about two concepts which are very important in calculus: limits and continuity. So what is a limit? Here is an intuitive definition. The limit of f of x as x approaches a is the value that f of x gets extremely close to as x gets very, very, very close to the number a. Keep in mind this is not a precise definition, but it is good enough to understand what a limit is. So let's take a look at a picture. Let's suppose that we have a coordinate plane, and in that coordinate plane we've got a line. Something like f of x is equal to x subtract 2. And we want to ask about the limit of this function. Here's some notation. We use LIM to represent limit, and underneath of LIM, we tell everybody what x is getting close to. So let's suppose x is getting close to the number 3. So we write LIM, and underneath x, and then a little arrow pointing at a 3. So that's read the limit as x approaches 3. And then we say what we're going to take the limit of, x minus 2. So what this is saying is what number does x subtract 2 get really close to as x approaches 3? Now we know that we have a point on this graph where x is equal to 3 and y is equal to 1. And if we come along this curve and allow our x values to get closer and closer and closer to 3, and we allow that from both sides, so we're sliding in from the left and sliding in from the right, we see that on both sides our y is getting really, really close to 1. So we say that the limit as x approaches 3 of x subtract 2 is equal to 1, because the closer x gets to 3, the closer f of x gets to 1. Now, based on our last example, you might be wondering, why do we bother talking about this limit thing? All it looks like she really did was plug in 3 and get back an answer, 1. Well, it turns out with some kinds of functions you can do that the limit value and the function value are the same as each other. But it turns out that it only happens with special kinds of functions. And one of those special kinds of functions is a polynomial. Polynomials have the nice characteristic that when you draw their graphs, nothing strange happens to the curve. As we go along, we can put our pencil on one end of the picture and we can keep on drawing until we get to the other end of the picture. We don't have to jump over any holes in the curve. There are no asymptotes, no kind of blank spots in it. So that means that, yeah, no matter what x gets close to, y is always going to get close to the value of that function at whatever number x is nearing. So polynomials are really easy to find limits of. So it's easy to find the limit of a polynomial function. What about a rational function? Rational functions are simply quotients of polynomials. And it turns out that most of the time rational functions are fairly easy to deal with. However, they have two features that we do not see in polynomial functions, namely holes and vertical asymptotes. So we need to think about what happens at those two features on these graphs. So let's suppose we have a rational function, f of x equals x divided by x squared subtract x. If we factor that denominator, we get x over x times x subtract 1. And thinking back to what you learned about rational functions in pre-calculus, we know that the common factor in the numerator and the denominator, x, that can be zeroed out causes a hole to occur in the graph. And other than that hole, the graph of f of x looks just like the graph of 1 over x subtract 1. So we know there's a hole when x equals 0, and if we take that 0 and plug it into 1 over x minus 1, we see that the y coordinate of the hole is 0, negative 1. So that's a spot where the graph of f of x doesn't exist, because f of x isn't defined when x is 0. Now, looking at 1 over x minus 1, we see that we still have a factor in the denominator that can zero out. If x is equal to 1, the denominator is 0, and because it cannot be canceled, we know that x equals 1 is the location of a vertical asymptote. So we have two special features in this graph that we need to be concerned about. Let's draw a quick sketch of f of x. So here we can see what f of x looks like. To the left of our vertical asymptote, x equals 1, we have a piece of the graph that lives below the x-axis. And to the right of x equals 1, we have a piece of the graph that lives above the x-axis. Now, let's think about this idea of a limit. If I pick a spot anywhere on the portion of the graph that's to the right of x equals 1, if I allow x to get closer and closer and closer to the x-coordinate of that point, I can see that y is getting closer and closer and closer to the y value of that point. So I have no trouble finding the limit if I'm on the right-hand segment of the graph. If I go over to the left and I pick a point, again, I'm going to see the same behavior. And the only thing I might worry about over here is what about that hole? But if I come towards the hole from the left-hand side and from the right-hand side, both things agree that if I were allowed to plug 0 into f of x, I should get back negative 1. So I can see that the limit as x approaches the x-coordinate of the hole is simply the y-coordinate of the hole. So the limit exists at the hole. So that means my one and only problem is the vertical asymptote. Vertical asymptotes mean that the function is either decreasing with no boundary or increasing with no boundary. So that's a special kind of not having a limit. So we can see that this rational function doesn't have a limit as x approaches 1 because it's unbounded there. So now we've taken care of polynomials and rational functions, let's talk about trigonometric functions. Trigonometric functions are nice. They act very similarly to polynomials and to rational functions. If we look at, say, the sine function is extremely well behaved. It just repeats itself over and over and over, forever and ever, and there are no weird asymptotes or holes or anything funny going on with that function. So the sine function, to find its limit, all you have to do is evaluate it, just like a polynomial. Same thing with the cosine function. Now we know that some of the other trig functions aren't as well behaved as the sine and the cosine. The tangent, the cotangent, the secant, and the cosecant all have vertical asymptotes. But as long as we stay away from those asymptotes, those pieces are well behaved too. So we will see the same thing happen that happened with our rational example. We'll be able to find limits everywhere except at the locations for those vertical asymptotes. So now let's talk about piecewise defined functions. This is where things can get interesting, because piecewise defined functions have a feature that we haven't seen before. Namely, they can have some big gaps in them that the other functions don't display that aren't caused because of asymptotes. So I'm going to draw a picture of a piecewise defined function so you can see what I'm talking about. So here's my piecewise defined function. F of x equals negative 1 if x is smaller than 0, and f of x equals positive 1 if x is greater than or equal to 0. Notice with this piecewise defined function, I've got two lines. I'm going to be in good shape anywhere except at 0. At 0, I change definitions, and so at that one point, I may have a hard time finding a limit. And it turns out that in this particular case, if I try to take the limit as x approaches 0 of f of x, it's not going to exist. Notice that as I approach 0 from the left, I keep getting -1, -1, -1, -1, so that makes the limit appear like it ought to be -1. But if I approach 0 from the right, my function keeps saying 1, 1, 1, 1, 1, so that makes the limit look like it ought to be +1. So the limit from the left and the limit coming from the right aren't agreeing with each other, and whenever that happens, the limit doesn't exist. So now we've seen several different things that can happen with these limits. As long as we stay away from these funny kind of gaps in our functions, these jumping up and down gaps that we see in this step function, or those vertical asymptotes we saw in our rational function and that we mentioned with some of our trig functions, we're not going to have a hard time determining our limits. Now, there are some other very weird kinds of behavior that we will see later on, but for right now, this ought to give you a pretty good intuitive idea of what a limit is. So now that we've talked about limits, let's talk about continuity. So what is continuity? Remember earlier I mentioned that polynomials were nice functions and that they were really well behaved because they didn't have any gaps in them, no holes and no asymptotes. It turns out that a polynomial exhibits this idea of continuity. A really quick way to get a handle on what continuity is to suppose you have a picture of some sort of function. So here's a function, probably a polynomial. Suppose I take my pen and I put it on one end of my function and I start tracing my function. As long as I can go from one end to the other and stay on that graph without having to lift my pen to jump over a hole or an asymptote or on one of those little jump up spaces, then my function is continuous. Now, of course, that's great if you can see the entire function, but most of the time our domain is something like the entire real number line, in which case we can't draw the whole picture, and so we cannot use this as a definitive test. But it is a good, quick way to get an idea of whether or not your function is continuous. Here are the actual criteria that have to be met in order to be a continuous function. First, the function has to be defined. Second, the limit of the function must exist. And third, the limit value and the function value have to be the same as each other. So that means in order for a function to be continuous at some specific value, we have to meet all three of these criteria. And in order for a function to be continuous over its domain, it has to meet all three of these criteria for every possible value in the domain of that function. So this is pretty strict. And when we check for continuity, we want to make sure that we do it in this order. So first, we always ask whether or not the function is defined at the point of interest. If the answer is yes, then we see if the limit exists. If the limit exists, then we move on to the last step and check and make sure the function value and the limit value are the same. If we get through all three stages, then we can go, yes, our function is continuous at this particular point. So let's take a look at a couple of example pictures. We're going to see if we can figure out where these functions are continuous and not continuous. So let's take a look at this first picture. Now, we're going to ignore the endpoints where we're starting and stopping the function for right now. We're interested in the interior. So the first place that I see a problem is right here. Because there's a hole, that means the function is not defined there. So this function fails to be continuous at 1 because we've failed on the very first criteria. The function is not defined. Now, everywhere in between 3 and 1, I see there are no troubles. Those values are all defined. We're not going to have any trouble finding a limit in there, and the limit value and the function value are going to be the same. When I'm moving from 1 to 2, again, I'm in good shape. Everything's defined in there, not going to have any trouble taking a limit, and the limit and the function value ought to be the same. Now, the next problem area comes right here at 2. Notice that there is a definition for the function at 2. It says that f of 2 should be equal to 2. But if we look at the limit as x approaches 2 of f of x, we're going to see something different. Sliding along the curve from both the left and the right, the value that we're actually approaching is the y-coordinate of the little hole. So we see that the function exists. It's defined to be equal to 2 at 2. The limit exists. The limit as x approaches 2 of f of x is 3. But we fail on the third criteria. The limit value and the function value are different from each other. So that means at 2, our function is not continuous. We can see that the same thing is going to happen when we get to 3. At 3, the function is defined to be equal to 0, but the left-hand limit is 0 and the right-hand limit coming along here is 1. So on that one, the limit fails to exist. So we have failing criteria number 1, failing criteria number 3, and failing criteria number 2. So each of these values, 1, 2, and 3, are locations of what we would call discontinuities. So here's the second picture. Pause the video and take a minute and see if you can write down where each of the discontinuities is in this graph and which of the 3 rules it fails. Remember, you want to make sure you start with 1 and then you're working your way up to 3. And then once you've got your answer, restart the video and see how you did. Okay, so let's see how you did. The very first discontinuity in this picture occurs at x is equal to 2. Taking a look at this thing, we see that the function is defined. F of 2 should equal 2, but we have a problem with the limit. As we come from the left-hand side, it looks like the limit ought to be 2. But as we come from the right-hand side, it looks like the limit ought to be 4. So, at 2, we're failing on criteria number 2. The next discontinuity occurs at 3. Notice there's a vertical asymptote there. So, that means our function is undefined when x is equal to 3, so we're failing on the first criteria. The third discontinuity is occurring at 4. The function is defined. It says that f of 4 is supposed to equal 2, and even the limit exists. As we approach from the left and the right-hand sides along our graph, both sides agree that we're getting really close to 4. But unfortunately, the function value and the limit value are different, so we're failing on criteria number 3. So there are 3 discontinuities in this graph, 1 for each of the 3 criteria. So at this point, you should have a good basic idea of what a limit is and what it means for a function to be continuous. Later on, we're going to go back and we're going to take these same 2 ideas and we're going to firm them up quite a lot and give some actual solid mathematical definitions for these things. But for right now, this intuitive idea is good enough to get us started.